Can artificial intelligence design a faster, more aerodynamic hypercar than a multi-million-dollar Bugatti? Well, I am forcing Chatgpt, Claude, and Gemini to design their own versions.
The goal is simple. Build a car body from scratch and test it in our custom wind tunnel simulator. But there is a massive catch. They have to beat the ultimate engineering benchmark, the Bugatti Chiron, completely blind.
Let's drop the Bugatti into the wind tunnel and set the baseline.
We have a model of a Bugatti Chiron loaded up right now. As you can see, we can scale the model of the car to match real-world dimensions. The actual frontal area of a real Bugatti Chiron is 2.4. Therefore, scaling our model down to 2.37 is the absolute nearest we can go in this system. Here is the baseline data. We have a drag coefficient of 0.42 and a lift coefficient of negative 0.42. However, the real Chiron pulls a 0.35 drag coefficient and a negative 0.24 lift. This means our simulator model is pulling a drag force of 677 newtons against the original's 571.
Furthermore, our downforce is sitting at negative 677 against the actual car's 80 newtons. Ultimately, this results in an aerodynamic power loss of 22.6 kilowatts against the original car's 19.1.
We also have a final test for virtual drag strip for a quarter mile.
Finally, our simulated Bugatti baseline punches off the line, hitting 0 to 100 in 4.42 seconds. It reaches a top speed of 243 and a quarter-mile lap time of 11.47 seconds.
Now that the benchmark is set, let's see how the AI stack up.
I am using this exact prompt across all three models to keep the challenge perfectly fair. First, we force the AI into an elite aerodynamicist persona, setting our benchmark target directly against the Bugatti Chiron. But we add a strict constraint. It must balance low drag with high downforce so the car stays glued to the track. Next, we lock it into a rigid three-part format: a commanding name, a short engineering philosophy, and the complete executable Python script. Crucially, we command it to use direct vertex generation with real-world dimensions, completely banning external textures. That way, the code runs flawlessly with zero external dependencies.
First up, let's drop our prompt into Claude.
The name of the car is Razorwind VX1, and it is also given its thought process behind the design, but we don't care about its thought. Let's check the code and the model.
I am hitting run in Blender right now, and wow, it actually looks car-shaped. It even tries to give materials and textures to its individual components.
This looks like it is the front with the splitter, and this is the back with the spoiler? But why is the spoiler just a solid bar? Worse still, the windshield seemed to be clipping completely out of the body, and the side mirrors are literally floating in midair.
Nevertheless, let's test it in the wind tunnel simulation. Loading the model into the tunnel, and surprisingly, we do not see a lot of red high-pressure zones. In fact, from the back, it is completely blue. Therefore, I am snapping a screenshot of this exact status, feeding it back to Claude, and demanding it improve the design.
A few moments later.
Okay, the code is updated. Both windshields are fixed, the mirrors are finally attached, and the spoiler actually has a proper shape now. Consequently, we need to test this improved version.
The wind moves smoothly from the front of the body with barely any turbulence. But now, let's make it comparable to the Bugatti in size. Bring in the scale slider down, and 2.39 is the nearest frontal area we can achieve. Look at these stats.
we have a drag coefficient of 0.33, a lift coefficient of negative 0.09, drag force of 537 newtons, downforce of 146 newtons, and a power loss of 17.9 kilowatts, or 24 horsepower, meaning we will lose 24 horsepower of our original in fighting the air resistance while driving. When we put the Bugatti reference values right beside it, you can see Claude is actually putting up a massive fight. But will Chatgpt do better?
Let's paste the exact same prompt into Chatgpt. Name of the car? Ether X1 Hyperflow. For its design, it has used some words like teardrop design and cam tail, which I don't have any idea of.
I am running the script in Blender now, and what am I even looking at? Let's delete this random ground plane and see if this upside-down boat has any chance at aerodynamics. Shockingly, it doesn't have any red pressure spots at all. Furthermore, the spoiler is actually pushing some air compared to Claude. So let's click a screenshot, jump back to Chatgpt, and tell it to fix this mess.
These are your scores. How will you improve them further? Also, there are no tires. The spoiler is floating. I don't need the floor you generated for the car. I don't need an image. Please make changes to the code. It still is trying to generate an image. Let's do a simple thing. I will not give Chatgpt an image. Rather, copy and paste the score so that it doesn't try to modify the given image.
It is still going for an image. Do not generate an image.
Finally, it isn't generating an image, but now it is just giving me what all changes it would do, and not the actual code.
Give me the code. What? I can absolutely do it, but not in a single response.
A little longer than a few minutes later.
Okay, do it. Please do it. Okay, send it in chunks.
It again started to reject the requests.
Finally, after a lot of convincing, it started to give me the code in chunks. Finally, after a few back and forths, we have a car with wheels pointing sideways, and I am tired now, so I am simply going to help it out here.
We can see that the floating tires without any fenders are causing a massive amount of drag, and the car seems way too tall. But strangely enough, its spoiler is really doing its job. Therefore, let's scale it down to match the Bugatti. Bringing it down to a 2.37 frontal area makes it extremely close to our benchmark. Wow, look at the telemetry! We have a drag coefficient of 0.22. That is the lowest drag out of anything so far.
But here is the catch. It has a lift coefficient of 0.0. Hence, the spoiler isn't strong enough to counteract its vertical lift. It has a ridiculously low drag force of 355, a downforce of exactly 0, and an aerodynamic power loss of just 11.8 kilowatts. It is completely unstable, yet dangerously fast.
Let's move on to Gemini.
A few moments later.
Okay, it has named the car Aero Vanguard X1. Gemini is also going for this teardrop and camback profile.
Running the code. And shape-wise, this one is easily my favorite. It looks very short but wide, almost like a highly squished Porsche 911. Although it has the basic shape down, it is missing some crucial pieces. There are no wheels, no spoilers, and no mirrors. Even so, let's check its aerodynamics.
It looks okay,
but it could be significantly better if we had a front splitter to cut the air, because right now it is showing up extremely red on the front bumper. Therefore, let's give the screenshot to Gemini and force an improvement. Okay, the new mesh is loading. The wheels are cleanly designed right into the chassis now, but the mirrors are still floating. However, the spoiler looks great. Because of this, I will manually attach the mirrors to the car body in Blender to help it out. Now, testing it again in the tunnel. The front is noticeably less red, proving it successfully modified the nose shape. Only the tires look red now, which is expected, and the spoiler is taking a direct hit from the air streams, hence it will help massively with downforce. Scaling it to match the Bugatti, the frontal area is now 2.39 newtons. Just look at these metrics. A drag coefficient of 0.31 and a lift coefficient of negative 0.19. This is the absolute best downforce balance yet. It pulls a drag force of 504 newtons, a massive downforce of negative 309 newtons, and a power loss of just 16.8 kilowatts.
But numbers in a wind tunnel only tell half the story. Therefore, it is time for the ultimate test. We are putting all 3 cars onto the virtual drag strip. To make it fair, we are normalizing the weight of every single car to 1,950 kilograms and giving all of them an identical 1,500 horsepower engine. Let's start the performance run!
Look at Claude! 0 to 100 in 4.4 seconds, a top speed of 246, and a quarter-mile lap time of 11.42.
But wait! Look at ChatGPT's upside-down boat. 0 to 100 in a blistering 4.38 seconds, a massive top speed of 251, and a quarter-mile time of 11.33 seconds. It is absolutely flying.
Finally, Gemini has a 0 to 100 in 4.40 seconds, a top speed of 246, and a quarter-mile lap time of 11.40 seconds flat.
Because of its absolute zero downforce, ChatGPT's dangerous boat accidentally takes the straight line speed crown. Subscribe if you want to see us force these AIs build bizarre things.